Hello everyone. I welcome all of you for the third session of drawing. In this session, we'll calculate drawing time for following the drawing period. Already we have discussed in previous session drawing time calculation in constant rate drawing period. So this session is dedicated for the discussion of following rate drawing period. Calculation methods for falling rate drawing period. In the falling rate drawing period, the rate of drying R is not constant but decreases when drying proceeds past the critical free moisture content Xc. On this axis we have the rate of drying and here free moisture content. Constant rate drying period and then falling rate drying period. Initial free moisture content is X1 and the moisture content where constant rate drying period ends is called critical free moisture content, right? And this is X2. From Xc to X2 we have falling rate drying period. Rate of drying is decreasing from a maximum or constant rate of drying Rc to 0. Rate of drying, the value of R is decreasing. When drying proceeds past the critical free moisture content Xc, rate of drying is Ls upon A dx upon dt. H unit kg of H2O per meter square drying surface area per R. X is kg of H2O per kg dry solid. Ls kg of dry solid. A exposed surface area, right? So you will get this unit of rate of drying. We are going to calculate drying time. So bring dt on left hand side minus Ls upon A dx upon R. Integrate both sides at t is equal to 0. Dear friends, now we discuss drying time in falling rate drying period. So remove this, and in this falling rate region, suppose initial moisture content is X1 and final moisture content is X2. So at time t is equal to 0, free moisture content is X1 and at time t free moisture content is X2. So this will give drying time for the reduction of moisture content from X1 to X2, right? By using property of definite integral, this minus interchanges limit of integration x2 to x1. Ls is constant taken outside of integration. A, here R is not constant. So it remains inside integration, right? So this is basic integral form of drying time in falling rate drying period. Drying in falling rate period by liquid diffusion of moisture. We have two mechanisms for moisture flow in falling rate drying period. Liquid diffusion theory, that is flow of moisture by diffusion of liquid, drying by the diffusion of liquid, and by capillary flow. So first we see drying in falling rate drying period by liquid diffusion of moisture. This type of diffusion is taking place in non-granular materials such as soap, gelatin, glue, and in the later stages of drying of free water in clay, wood, textiles, leather, paper, foods, starches, and other hydrophilic solids. In the later stages of these materials drying, and from the start to attainment of particular moisture content in such material, liquid diffusion theory is applied. Right? Such materials are non-porous. They don't have interconnecting pores for the capillary movement. Right? So, in such material, diffusion of moisture on the surface of material under drying takes place, and further evaporation of this moisture into drying gas happens, and finally we are getting dried product. Right? So this is differential equation for the liquid diffusion through non-porous material like soap, gelatin, glue. Here X is free moisture content. A small x is the distance in the solid. dl, liquid diffusion coefficient in meter square per hour, and t, time. Its solution is this. This is infinite series. It has infinite terms. For long time drying, if drying time is longer, it means the value of t is higher. If we put higher value of t in the power of e, you will see higher negative power. It means it comes in denominator of this one, e raised to power 9 dlt. So you will get a smaller value as compared to this. Here we have a 9, 25, and so on. So for longer drying, in constant drying period, if liquid diffusion theory is guiding, we can write approximately this relationship by neglecting other terms without sacrificing too much accuracy. इससे जो है ना एक्यूरेसी में हमें कोई प्रॉब्लम नहीं होगी. बहुत ज़्यादा जो है ना रिजल्ट एक्यूरेट से डिफरेंट नहीं होंगे. Dear friends, here each and every terms is known. X, free moisture content after time t. X1, initial free moisture content. A small x1 is thickness of slab of soap like material, gelatin like, glue like, thickness of slab upon 2 if drying is taking place on both sides. If drying gas is flowing over top and bottom, so in that case, a small x1 is thickness of slab upon 2. If drying is taking place from one side, suppose drying gas is flowing on the top only, so x1 is equal to thickness of material, because liquid water has to move from bottom to top. Only drying is taking place at the top. So from here to here to here, right, liquid has to travel. So here x1 is T. If drying of soap slab is taking place on both sides, top and bottom, so half is controlled by this and half is controlled by this. So x1, right, half of liquid, half thickness, liquid of half thickness moves in this direction, and liquid inside this soap slab in this half portion will move in this direction. So movement of liquid water in slab in this case is thickness upon 2. But here drying is taking place from one side only. तो सबसे नीचे वाले लिक्विड को कितना डिस्टेंस ट्रेवल करना पड़ेगा? टोटल थिकनेस के इक्वल, राइट? So friends, x upon x1 for long drying time, only the first term in equation is significant. So x upon x1 is equal to 8 pi square e raised to the power minus dlt pi upon 2 x1 whole square, right? E raised to the power minus dlt pi upon 2x1 whole square is equal to x pi square upon 8x1, right? 1 upon e raised to the power dlt pi upon 2x1 whole square is equal to this e raised to the power. So we'll get inversion here, right? Taking natural log on both sides, so dlt pi upon 2x1 whole square is equal to ln natural log 8x1 pi square x. Drying time t is equal to 4x1 square upon pi square dl ln 8x1 pi square x. So guys, if liquid diffusion is guiding drying in falling rate drying period, so from x1 free moisture content to x free moisture content, right, this is the amount of moisture reduction. For this amount of moisture reduction in falling rate drying period, this is time taken. So we can usually apply this formula. Just memorize this result. और इजीली जो है डेटा को पुट करेंगे और आंसर आएगा. Here rate of drying in falling rate drying period, this is falling rate drying period, R is decreasing. Rate of drying is a function of x. X decreases, R decreases. So we are interested to calculate a rate of drying at time t. At time t, this is the free moisture content x. We are going to calculate a rate of drying at time t after a start of drying in falling rate drying period. Falling rate drying period में drying start होने के t टाइम बाद rate of drying क्या होगा उसकी कैलकुलेशन, माइनस ls अपॉन a dx upon dt. This is rate of drying at any time. Find dx upon dt, put the value here to get the rate of drying at time t. So guys, differentiate this expression with respect to time, we will get dx upon dt. I am not here to teach you differentiation. This is not mathematics class, and this is not BTech like mathematics. Right? Already We have learned in 11 12 class. So dx upon dt is this minus pi square dl x 4 x1 square. This x is free moisture content at time t. So putting the value of dx upon dt here, we can calculate the rate of drying when moisture content is x, right? In falling rate drying period. So this is the result. Problem based on this concept. The diffusion coefficient of moisture in a given wood is 2.97 into 10 to the minus 6 meter square per hour. Large planks of wood 25.4 mm thick are dried from both sides by air having a humidity such that the equilibrium moisture content in the wood is this kgH2O per kg of dry wood. The wood is to be dried from a total average moisture content xt1 this to xt this. Calculate time needed. So this is formula. Initial pre-moisture content. This is pre-moisture content after time t. So time taken for the reduction of pre-moisture content x1 to x is t. This is required. x1 because here drying is taking place from both sides of planks of wood. Thickness of plank is 25.4 mm. Convert this into meter by dividing this 1000, right? And x1 is thickness by 2, 25.4 by 10 to the power 3 in meter by 2. So this is x1. xt1 is given. Total moisture content initially is given, right? This is 0.29. So 0.29. So we can calculate x1 initial free moisture content, total moisture content minus equilibrium moisture content, right? 0.29 minus 0.04, right? So here we have initial free moisture content, and similarly final free moisture content is final total moisture content minus equilibrium moisture content, this, right? So we have x1 x small x1 dl is given in the problem in meter square per hour. Put these values and get the answer in hour, right? Dear friends, if drying in falling rate drying period is guided by capillary action, right? So for such problem we are going to calculate drying time for reduction of free moisture content x1 to x2. Water can flow from regions of high concentration to those of low concentration as a result of capillary action rather than by diffusion if the pore sizes of granule materials are suitable. In non-porous material like soap, gelatin, glue, right, we have no interconnecting pores, so capillary action is not happening in such materials. But we have granule materials or porous materials, so pores are suitable for the capillary flow from inner of the material to the surface, right? The capillary theory assumes that a packed bed of non-porous spheres contains a wide space between spheres called pores. अगर अपने पास पोरस मटेरियल है कोई दिक्कत ही नहीं है, और नॉन पोरस ग्रेन्स है तो ग्रेन्स के बीच में पोर्स बनेंगे, right? As the water is evaporated from the surface of material under drying, so there is a concentration difference between water at the surface and water inside the material, right? So this difference causes capillary action. capillary flow from the inner to surface, and where surface drying is taking place, continuous evaporation is taking place, right? As water is evaporated, capillary forces are set up by the interfacial tension between the water and solid. These forces provide the driving force for moving the water through the pores to the drying surface. If the moisture movement follows the capillary flow, the rate of drying R will vary linearly with X. So here R varies linearly with X, right? If moisture movement follows capillary flow, if moisture movement is induced by capillary action, in that case, we assume drying is linear function of free moisture content, right? So here, in this case, we have two different possibilities. Constant rate drying, and this is falling rate drying period. Here R is varies with X linearly. So here this rate of drying curve is passing through origin, and this is in the intercept form. So these are two possibilities. One where a straight line is passing through origin, and here we have cut on R axis. For this we can write R is equal to AX, and for this we can write AX plus B, intercept form. Equation of a straight line passing through origin, y is equal to mx, y is R, m is A, slope of this line, here it is theta, then A is equal to tan theta, right? Dear friends, this is x1 and this is x2, both are less than xc. If x1 and x2 are less than critical moisture content, so actually we are calculating time required for the reduction of moisture from x1 to x2 in following the drying period, right? We can write RC is equal to AXC. If we put the value of X is equal to XC, then R becomes RC. At XC, R is RC. At X1, R is R1. At X2, R is R2. So here rate of drying is reducing as free moisture content reduces. At critical moisture content, rate of drying is RC. At free moisture content X1, rate is R1. At free moisture content X2, rate is R2. And here we have R is equal to X, general equation of this straight line passing through origin, or drying rate and X relationship during drying. So if X is equal to XC, R becomes RC, AXC. So from this we can write slope of this line is RC upon XC. Similarly, R1 upon X1, R2 upon X2. So all RC upon XC is equal to R1 upon X1, R2 upon X2, and they all give same result, slope of this straight line passing through origin, right? So guys, already we have established this relationship. LS is equal to T is equal to minus LS upon A, X1 to X2, dx upon R. This minus interchanges limit of integration, right? And dx R is AX, LS AA. A is the slope of line and it is constant taken outside of integration. X2 to X1, dx upon X, LS AA, ln X1 upon X2, right? A1 is equal to AX1 R1 is equal to R2 is equal to AX2. So X1 upon X2 is equal to R1 upon R2. So another form, ln R1 upon R2. Dear friends, in place of A, we can write ls RC upon XC. So XC comes in numerator, ARC. Ln X1 upon X2 or ls XC upon ARC into ln R1 upon R2. So this is drying time for the reduction of free moisture content from X1 to X2 in following the drying period if this drying is following capillary flow theory for porous and granular materials. Porous has interconnecting pores, and between grains we have interconnecting pores. So interfacial forces acting between surface of grains and water continuously on the surface. Drying gas is evaporating liquid, so concentration on the top is lower, concentration at the surface of material under drying is lower than concentration inside the material. So this difference causes flow of liquid from interior to surface by capillary action. Dear students, suppose we have slab like material, right, and x1 is its thickness, and drying area is A, so its volume A x1, and dry density in kg per meter cube is rho s. So ls kg of dry solid we have calculated, total kg of dry solid. So in place of ls we can write this relationship, rc. We can easily calculate rc. Constant rate of drying is also involved here because critical point is common to constant rate drying period and falling rate drying period. Constant rate, and this is falling rate drying period. So this rate of drying is called constant rate drying period, and here we have a critical free moisture content. So this point is common to this and this, so that we are involving this RC in calculation in free moisture, calculation in falling rate drying period. RC, we know RC. How to find RC? From constant rate drying theory, RC is convective heat transfer from drying gas to thick layer of liquid on the surface of material under drying upon exposed surface area into latent heat of vaporization at wet bulb temperature. Already we have discussed these all things. Convective heat transfer from the drying gas to thick layer of liquid on the surface of material under drying. H, heat transfer coefficient, exposed surface area of material for drying, temperature of the drying gas, that is called dBT, and temperature of the liquid on the surface of material under drying is TW. This TW is called wet bulb temperature of drying gas, A lambda watt. Another definition by using mass transfer, mole fraction of water at the surface, which is at wet bulb temperature, mole fraction of water vapor at the surface, mole fraction of the water vapor in the moist air or in the drying gas, mass transfer coefficient. This is molar flux into area. This is mole transfer rate, molecular weight of water vapor. This is kg per time, mass transfer rate, and this is latent heat of vaporization in kilojoule per kg. This is kilojoule per unit time heat transfer divided by A into lambda W. Right. So guys, cancel each other, and RC is H T minus TW. No need to remember this formula. If you have concept, if you have mechanism, what is actually happening here, then we can easily memorize this entire relationship. कोई एफर्ट नहीं लगेगी. एंड ट्रांस सीजी में आप लोग यही सब सीखते हो. क्या सीखते हो? रटना कम है, कॉन्सेप्ट से ज़्यादा लर्न करना है, तभी 80-85 मार्क्स आते हैं. अदरवाइज 50 से ज़्यादा मार्क्स नहीं आएंगे. ट्रैक चेक कर लेना, रिकॉर्ड चेक कर लेना. वो टीचर जो खुद 50 लाया था, जो रट के पढ़ाता है, उसके स्टूडेंट भी 50 से ऊपर नहीं लाए होंगे. ढूंढना, सब सर्च करना. डियर स्टूडेंट्स, और अनदर फॉर्म में क्या हो जाएगा ये? एम ए वाई y w minus y. Here we have difference in mole fraction. We can convert this into a specific humidity. 1 kg dry air contains h kg water vapor if this mixture has a specific humidity h. If this mixture of dry air and water vapor has a specific humidity h, the unit of h is kg of water vapor per kg of dry air. So 1 kg dry air contains h kg water vapor. So now we easily define mole fraction of water vapor. H upon molecular weight of water. This is the mole of water vapor in this mixture. H upon Ma. This is moles of water vapor plus total moles of components in this mixture, and 1 kg air, mass of molecular weight of air. Here H is in the order of 0.02, 0.01, and here we have 1, 18.02, 28.97. So guys, we can neglect this if we compare this term with this. For simplicity, we are neglecting this. So H mb upon ma. Mole fraction of moist air just above material under drying which has thick layer of liquid. It denoted by this. A specific humidity at wet bulb temperature, or a specific humidity of moisture near the surface of material under drying which has thick layer of liquid. Exactly, this is condition of wet bulb temperature measurement. mb upon ma. So if we put these values from this equation, so we will get mb ky hw minus h. Right? So in this way, guys, we can calculate each and everything. What is linear function of x? If both x1 and x2 are less than x2 and not passing through the origin. So this is the situation. Right? So here we have r x plus b, rc axc plus b, r1 x1 plus b, r2 ax2 plus b. Dear friends, r1, take the differences. So r1 minus r2 upon x1 minus x2. This is a here. Right? So guys, in this situation, drying time, ls upon a dx upon r means ax plus b, x2 to x1 minus makes this interchange of limits. ls upon a ln ax plus b, 1 upon x plus b. Sorry. ls upon a, and integration is ln x plus b upon a x2 to x1. ls a ln ax1 plus b, right, upon ax2 plus b, right. x1 plus b is r1, x2 plus b is r2. ls a ln r1 upon r2. Here a is this. So ls x1 minus x2 a r1 minus r2 into ln r1 upon r2, right. So guys, this is all about falling rate ड्राइंग पीरियड. आगे के सेशन में और चीज पढ़ेंगे, तब तक के लिए सेशन को यहीं पर स्टॉप करते हैं. आई होप आप लोगों को सेशन अच्छा लगा होगा. अच्छा लगा है तो जो है ना, टिल द गेट एग्जामिनेशन रिवाइज करते रहिए और हमेशा माइंड में रखिए. फ्यूचर के लिए ना रखिए कि हम गेट के टाइम में रिवाइज करेंगे. वेस्ट ऑफ सेशन यार.